This is an introduction to exercise 11.1 on continuous probability distributions. We've learned about our discrete probability distributions. We're going to focus on our continuous, with the key factor, of course, being the type of data we're focusing on. So a reminder, discrete is a whole number, or not specifically a whole number, but a calculable number of values it could be. So for example, shoe sizes, number of siblings, etc. A continuous distribution, we're focusing on the fact that it could be any range of values, or a incalculable amount of values it could take place as. Again, just like our our discrete, there is a certain value, a certain set of conditions we have to fulfill. With a continuous random variable, as we said, is a range of variables it could be. There are two conditions it must be met. Well, actually three, but we'll get to the third, less obvious one in a moment. F of x is greater than 0 for all x in the specified domain, which basically just means for our function, of course, the probability needs to be greater than 0 or equal to 0. Right? It obviously can't be a negative value. You know that. The second one is that the area under the graph is summing to 1 or adds up to 1. Now, in mathematical notation, that would just look like this. And if you could just copy this down, that's all we're looking for. Integral, or the sum of all values from negative infinity to infinity of f of x, adds up to 1. Pretty straightforward. The last one, which is less of a condition and more of a statement, is this one right here, where the probability of x being between a and b is equal to, from a to b, f of x dx. Which just means the probability of something being, for example, between 1 and 2 is the area of the graph under 1 and 2. 1 to 2, sorry. That's all it's saying. Any questions? Let's move swiftly on. Suppose that the random variable x has the probability density function with the rule, etc. Now, f of x is equal to c times x if it's between 0 and 2, and 0 elsewhere. So this is a piecewise function. I'm going to assume that we are familiar with them already. Find the value of c that makes f a probability density function. This kind of question really is just relying on the fact you know your conditions. Of course, the total of the area under the graph needs to be 1. So all I need to do is write, and I'm going to write it out as I would write on an exam. So as negative infinity to infinity, that should be infinity, not sideways 8. There we go. Of f of x dx equals to 1 from 0 to 2, because my function is really only existing from 0 to 2, right? I don't really care about elsewhere. So from 0 to 2, c times x dx needs to equal to 1. So that's how I would write it out in the exam. Of course, I haven't finished. I haven't found the value of c. Of course, that would equal to, and I'm just applying my anti-differentiation rules. C to the power of x would anti-differentiate into cx squared over 2 from 0 to 2, which gives us an answer of 2c. Therefore, c equals to a half, because I'm just saying 2c equals to 1. Find the probability as x is greater than 1.5. Of course, we're going to use the same idea. Of course, not going from we're not going from 1.5 to infinity, because that wouldn't make sense. We're going from 1.5 to 2. If we go from 1.5 to infinity, yes, you're right. The function only exists till 2, and then afterwards it's 0, right? But if we put in, for example, we write this 0.5x dx and we replace the 2 with infinity, that's implying that our function goes towards infinity, which means it would be incorrect. So we're just going from 1.5 to 2, which is my interpretation of this question. Okay? Solving that, we end up with 0.5x squared over 2, 1.5 to 2. I'm assuming we're able to do this, it's integration, and then with a calculator, 0.4375. With probability in methods, we're going to try our best to keep it in either exact value decimals or fractions, right? Typically, decimals is a little bit easier to interpret. So 0.4375, which tells us that this function, or this random variable x, has just under half the probability, about 50%, or just under 50% chance of being greater than 1.5. Something that I want to cast your mind back to regarding the area, or rather this section here, the probability of x being greater than 1.5 is pretty much the same as the probability, not pretty much, it is the same as the probability of x being greater than or equal to 1.5. Something to keep in mind, but the area under a graph at only one point is essentially 0. Okay. The time in seconds that it takes a student to complete a puzzle is a random variable x with the density function given by etc, etc. So we've got f of x equals to 5 over x squared. 5 over x squared from x being greater than or equal to 5 and 0 otherwise. Find the probability that a student takes less than 12 seconds to complete the puzzle. So again, I'm going to write my interpretation out in mathematical notation. So that becomes the probability, the probability of x being less than 12 equals to, from 5 to 12, 5 over x squared dx. Less than 12 seconds, so 5 to 12 seconds. Of course, this is implying that a student shouldn't take less than 5 seconds to complete this. This equals to 5 with the square brackets to indicate integration. 1 over x, 5 to 12, which is 7 over 12. Okay. Let's keep going. Find the probability that a student takes between 8 to 10 seconds, or 8 and 10 seconds, sorry, to complete the puzzle, given that he takes less than 12 seconds. So, given that question, we're finding the probability of 8 being less than x being less than 10, given that the probability, sorry, not probability, it's straight to the actual, here we go, x value, x being less than 12. Which would equal, because it needs to be an overlap, doesn't it? So it's a probability of x being, well, let's try that again, between 8 and 10 over the probability of x being less than 12. The overlap is just that first one, which ends up being equal to, from 8 to 10, of 5 over x squared dx over 5 to 12 of 5 over x squared dx. The numerator, of course, is from 8 to 10, the denominator from 5 to 12. We're going from 5 to 12, not 0 to 12, because that's what our function originally defined it as, which gives us an answer of 3 over 14. Any questions about that? Alright, last page. A couple of things I want you to write down at the top of the next page. Here we go. Properties of the continuous distribution. To find the mean or expected value of x of a continuous random distribution, we use the same method as before, where we have e of x, or the expected value of x, equals to, from negative infinity to infinity, of x times by a function dx. Right? That's actually the same formula, pretty much, as you had prior. A couple of things I'd like you to write down. One of them is just a general reminder. I'll write it up here. A reminder, e of g of x does not equal to g of e of x. Let's erase that. There we go. E of x. Just a general reminder. The second one, I'm not going to write that down. I'll write the third one down. So this one is also just another reminder. E of x, or e of, let's fix that up. Apologies, my computer's a little bit laggy today. I'll write down here. E of ax plus b equals to a times e of x plus b. Alright, so 2 just brief reminders for us to do. Okay, let's look at our example. Find the expected value of the random variable x, which has a probability density function with the following rule. Now it says f of x is, we've already done this one, from 0.5x from 0 to 2. So the expected value of x is just going to equal to, from negative infinity to infinity, of f of x multiplied by the x to give us that. In this particular scenario, that will look like this, which equals to, from 0 to 2, of x times 0.5 x dx. We can take out the 0.5, which gives us 0.5 multiplied by the integral from 0 to 2 of x squared dx, which gives us an answer of 4/3. So that's the expected value. Okay. For the same function, find the expected value of x squared. Again, it's the same principle as we apply in our discrete. The expected value of x squared, and this will be a general principle, is going to be from negative infinity to infinity, of x squared multiplied by f of x dx, which gives us an answer of 0.5 from 0 to 2 of x cubed dx, which gives us an answer of 2. Last question. The expected value of e to the power of x. Again, similar principle. We're going to the e to the power of x. I'm going to use a capital X here instead because that's what the question specifies. Which equals to, from negative infinity to infinity, of e to the power of x f of x. That's just the general application in this scenario. A specific application of that would look like equals to, from 0 to 2, because and our function is 0 to 2, e to the power of x multiplied by 0.5. I think you get the idea now. Which would equal to 0.5 of, from 0 to 2, of ex multiplied by x dx, which, using a calculator, is approximately 4.195.